This video discusses oblique asymptotes. The line y equals mx plus b is an oblique asymptote, or sometimes called a slant asymptote, of the graph of a function f if f of x approaches mx plus b as x approaches infinity or negative infinity. Please note that a rational function will have an oblique asymptote if the degree of the numerator is exactly one more than the degree of the denominator. That's really important to remember because that's the only time an oblique asymptote exists. Like a horizontal asymptote, the graph of a function may cross an oblique asymptote, just not at the end. So one of the ends has to tend towards the oblique asymptote. Well, how do we go about locating oblique asymptotes? Since the degree of the numerator will be one larger than the degree of the denominator, we can actually perform division. So we'll divide the numerator of the function by the denominator. The quotient will always be linear because the degree of the numerator is exactly one larger than the degree of the denominator. Remember that the degree of the quotient is the degree of the dividend minus the degree of the divisor. So if they always differ by 1, we're going to be left with a quotient of degree 1. So our quotient will look something like mx plus b plus some remainder. We're then going to drop the remainder. The line y equals b is the oblique asymptote for the graph of f. So basically, we're going to divide, drop the remainder, but keep the linear term and constant term. Y equals those terms will be our oblique asymptote. And an oblique asymptote is a diagonal line, just like y equals mx plus b produces a diagonal line. That's what oblique asymptotes are. So let's locate the oblique asymptote of the given rational function. The first thing you want to do is confirm that the degree of the numerator is exactly one larger than the degree of the denominator. It is. So we can divide. Notice that our divisor is x minus 2. Therefore, we can use synthetic division to perform the division. The 0 of the divisor on the outside, the coefficients of the dividend underneath, and then we synthetically divide. Our last number is always our remainder, but we are going to be dropping the remainder. Let me explain why. If I wasn't doing oblique asymptote and I was just doing regular division, I would end up with x plus 5 plus 12 over x minus 2. I want to focus just on this remainder part. Think about what happens to this remainder as x approaches infinity. As we plug larger and larger values in for x, the numerator is going to stay 12, but the denominator is going to become a larger and larger number. And we talked in our horizontal asymptotes video that when you have a small numerator, but your denominator continues to grow, the overall value of the fraction gets smaller and smaller and smaller. This remainder approaches 0. Since it's eventually going to be worth about 0, we just drop the remainder. So we're going to drop the remainder, and then our oblique asymptote is at y equals the linear and constant term. So y equals 1x plus 5. Note that a horizontal asymptote and an oblique asymptote can never occur at the same time. In order for an oblique asymptote to exist, the degree of the numerator has to be 1 greater than the degree of the denominator. When thinking about horizontal asymptotes, if the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Therefore, an oblique asymptote and a horizontal asymptote cannot exist at the same time. Any of the others can exist at the same time. You can have vertical with horizontal, vertical with oblique, just not horizontal with oblique.